We want to think about thermodynamics in organic chemistry, maybe differentiate how we think about it from how maybe we thought about it in general chemistry. In organic chemistry, mostly we're just asking whether or not a reaction is favorable or not. And we could say, does that mean it's uphill, unfavorable, or downhill, favorable? And so if we have a hypothetical reaction like this, we might just, by inspection, ask some questions about the reaction. And so we see that there's a bond here in the starting material that does not exist in the products. There's a bond here in the products that does not exist in the starting material. So we've got a bond broken and a bond formed. And so how strong is that bond? In general chemistry, maybe you'd look up these bond dissociation energies and do a calculation. We're just going to say, hey, this is a strong bond, and this is a weak bond. And so by making such an observation, we know that this aspect of the reaction, not necessarily the reaction overall, but this aspect of the reaction is unfavorable. So that bond breaking and forming makes an unfavorable contribution. We might also think about some of these other species that are participants in the reaction. And so maybe B minus, whatever it is less stable than Z minus. Well then, that's a favorable contribution. So we have something favorable and something unfavorable about this reaction. Now these are aspects of the reaction that we might determine without numbers. Okay, so maybe we'd use things like, hey, what's the size of that atom anyway? What orbital is involved? What are the electronegativities? Is there any resonance? These are factors that we would consider to think about whether or not those were favorable or unfavorable. And so these might make contributions to delta H, enthalpy. Don't forget, there's also this thing, delta S, which is entropy. And we'll make very qualitative arguments also about entropy. And so maybe if we have two objects, two reactants going to two reactants, we'll say, hey, that's the same, so delta S is around 0. If we have one going to two, well then that would be favorable. If we have two going to one, well that would be unfavorable. So we have two going to two here, so delta S is probably a small contributor to the overall favorability or unfavorability of this reaction. Remember that what we're applying here is the concept, delta G equals delta H minus T delta S, right? So everybody remembers that equation. And hopefully we all remember that delta G equals negative RT ln KEQ. So we got to think about equilibrium constants. And so if the equilibrium constant is equal to 1, well then delta G equals 0. An equilibrium constant greater than 1, remember that means there's more products than starting materials. Equilibrium constant less than 1, that means there's more starting materials than product. Okay, so hopefully we have those numbers in mind. We also have some special equilibrium constants. So you'll remember HA, an acid, might dissociate to a proton and A minus. And so remember that's the conjugate base of this acid. This acid is the conjugate acid of this base. And we have a special equilibrium constant called Ka for that sort of reaction. And pKa is the negative log of Ka. So Kas are often unwieldy, so we use pKas to communicate acid and base strength. And so let's compare two acids the way an organic chemist would. So if we had XH, maybe we would say the pKa is 10. and we have YH, and the pKa is maybe 5. So the question is, how much stronger an acid is XH versus YH? And the answer is not twice. The answer is 100,000 times more acidic. 10 to the 5th. That's a logarithmic scale. And that's what we have to remember about pKa.